Hello, everyone. Welcome back to the part two of the lecture. In the part one, we discussed about the correlation analysis, where we discussed about the importance of a scatter plot, how to measure the linear association and nonlinear monotonic association, and how to test hypothesis concerning population correlation. In this part, we will discuss about regression analysis. In this slide, I have summarized some of the uses of regression analysis in engineering field. What are the uses of regression analysis? We use regression analysis for several purposes, right? For example, to describe relationship between one response variable and several, one or more explanatory variables. And also we use regression to predict future response value for a given set of X values. And also we use regression analysis to estimate the effects of a response variable on different explanatory variables. To identify important factors related to a given response variable, uh, to study how uh, the, the, the effect of some variables can be studied by controlling for other variables, and also forecasting. Forecasting usually comes in time series analysis, but in regression, we usually talk about the prediction. And also, regression is used in process improvement and quality control also. So just to give you some examples in engineering fields, uh, as a method for describing relationships, for example, studying how the compressive strength of a concrete changes with the water cement ratio. Right. So we'll have to study how the concrete strength of concrete uh, relate to the water cement ratio. If you consider a prediction, for example, predicting the surface roughness of a mechanical part using cutting speed, feed range, and depth of cut. So these are several variables again, uh, predicting the surface roughness. So that is the response, and there are the other variables are the explanatory variables. Estimating the effect of variables. For example, estimating how much the fuel consumption of an engine changes when engine speed increases by 100 RPM. Right. So that is the effect, the size of the effect, and identify important factors. For example, identifying whether welding current, welding voltage, or welding speed has the greatest effect on the strength of the welding joint. Uh, as an example for controlling for other variables, studying the effect of current time on concrete strength while keeping cement content and water content ratio fixed. Uh, as an example of forecasting, forecasting the electricity demand of a factory using past energy consumption and production volume. So it's very similar to a prediction actually. And then as an example of process improvement and quality control, studying how temperature, pressure, and cooling rate affect the diameter variation of manufactured plastic pipes. Right? So in all these examples, uh, regression analysis can be used. So what is a regression analysis? In regression analysis, what we do is we try to find out a mathematical relationship, right? Earlier in the correlation analysis, we found out whether there are relationships and what kind of relationships and so on. In the regression analysis, what we do is once we find out that there is some relationship, we try to find out a mathematical formula to describe that relationship. So this function that we are going to write down is going to be a function of our x variables, right? So it can be considered as a function of x, where this x can be only one x, or it can contain several x's. So suppose this function is f. So it's a f of x. When we write down this function in terms of x, it includes some parameters, right? Or coefficients of individual x's, x values, right? So on the left-hand side, it will have some function of y. On the right-hand side, uh, it has several x's connected using some coefficients. So these coefficients are called regression parameters, right? So if these parameters are linear, that means they have power 1, then that regression function is called a linear regression model. Linear regression model. So this is, as I mentioned in part 1, there is a difference between the word, the meaning of the linear in correlation analysis and regression analysis. In the correlation analysis, what we mean by linear is a straight line relationship between x and y. We were considering only one y and one x. So when you plot y versus x, if the points are scattered around a straight line, then we say there is a linear relationship. On the other hand, in regression, we say there is a linear regression model, right? We are using a linear regression model. If the regression model, when we write down fx in terms of these several x's and corresponding betas or parameters, if the parameters are appearing with power 1, right, then we say we have a linear regression model. So it is not necessarily a straight line, right? When you have one variable, it may be even a curve. For example, y is equal to beta naught plus beta 1 x square, right? So that is a quadratic function in terms of x, but it is a linear function in terms of the parameters. So therefore, we call it a linear regression model. I'll give some examples uh, as I have shown here. So if at least one parameter in the regression model fx is nonlinear, right? In the nonlinear form, then the regression model is called a nonlinear regression model. So for example, if you say fx part, fx is equal to beta naught plus beta 1 x, where here x is, there is only one explanatory variable x. So this is called a linear regression model because this function is linear in terms of beta naught and beta 1. You have beta naught to the power 1, beta naught, beta 1 to the power 1. So in that sense, this is a linear regression model. On the other hand, this is also a straight line. So this straight line model is a particular example of a linear model. On the other hand, if you consider, for example, suppose you have an explanatory variable denoted by u, then suppose the model that you are going to consider is fx is equal to beta naught plus beta 1 u square. So in terms of u, this is a quadratic function. It's not a straight line. But this is a linear model because the parameters beta naught and beta 1 are appearing in the linear form, right? And if you denote this u square by x, still this is a linear regression model. Now this is a straight line in terms of x, right? It's a straight line in terms of x. So these are all examples of actually what you call simple linear regression models because there is only one x here, right, in all these things. Let's look at the next one. Suppose you have a variable denoted by v and you are going to fit a model like this, fx is equal to beta naught plus beta 1 e to the power v. Right? So this function is not a straight line in terms of v, but it is a linear regression model because the coefficients, regression coefficients are in the linear form. So it's a linear regression model. And again, if you denote this e to the power v by, say, for example, x, then the same model, we can say it is still a linear model, linear regression model. And it is now also a straight line as a function of x. But as a function of v, it is not a straight line, right? So therefore, a linear regression model doesn't have to be a straight line just because the word linear is there. The word linear means it's linear in terms of the coefficients. Right? Here, this is another example. Fx is equal to beta naught plus beta 1 log w. So w is the variable, explanatory variable. Actually, here we are considering it as a log of w. So this function is not linear in terms of w, but it is a linear regression model, right? It's a linear regression model. Yeah. And if you take log w to be, for example, x, you can call it still a linear regression model. Now it is a straight line model in terms of x, but it's not straight line in terms of w. And similarly, fx is equal to beta naught plus beta 1 divided by z, right? So in terms of z, this is not a straight line, but it is a linear regression model because the coefficients are in the linear form, beta naught, beta 1. And if you denote 1 over z by x, again, you can convert it into a straight line model also. But converting into a straight line model is not necessary always, right? Right. So these are some simple linear regression models. Simple linear regression models. In that case, you have only one x. So if you have more than one x, then it can be, for example, a function of x1 and x2, and it can be like this. So this is just again a linear regression model. It's a multiple linear regression model now. Multiple linear means because multiple word multiple comes because we have several x variables. Linear because it is linear in terms of betas or coefficients. If you consider a larger model like this, suppose you are considering three variables, explanatory variables, and a model like this, right? Beta node, beta 1 times x1, beta 2 times x2, beta 3 times x3. And then you also have the product terms, for example, x1 times x2, x1 times x3, and x2 times x3. That is also a multiple linear regression model, including main effects, we say x1, x2, x3, main variables. And then these are usually called two-factor in this case, it can be factor variables, interactions. Generally, this kind of things are called interactions, or we can call it products. So this situation actually we have in this case, this function is a linear. I mean, it's a flat surface. It's a surface, not a line or curve. It's a surface. This is also a surface, right? You have two variables. So these are three. You can depict this function using a three dimension as a surface, but it's not a straight line, a straight surface now. It's not a flat surface, whereas this one will be a flat surface. but both are multiple linear regression models. Now, this is even a larger model. It contains x1, x2, x3, and products. And in addition to that, it contains square terms also. Right. So that is also called a second order multiple polynomial regression model. But in general, it's a multiple linear regression model. Right. It's a special name because it has second order terms and these square terms and so on. It has a particular name, but this is also a type of multiple linear regression model because the coefficients are in the linear form, right? So this beta node, beta 1, beta 2, beta 3, beta 1 is a different is a different coefficient and so on. They all have power 1. On the other hand, if you consider, for example, these two functions, fx is equal to beta node divided by beta 1 plus x, right? So these are the same as beta node times beta 1 plus x to the power minus 1, if the whole thing. So that if you expand, for example, you will see that it contains beta 1 and beta 1 to the power negative 1, beta 1 to the power negative 2. That kind of powers will be appearing for the same parameter. So therefore, it's not a linear regression function. It's a non-linear regression function. And for example, this one also, if you consider beta naught plus e to the power beta 1x. So this e to the power beta 1x can be expanded using, for example, tail expansion. It's going to be 1 plus beta 1x plus beta 1 square times x square over 2 plus beta 1 cube x cube divided by factorial 3 and so on. So for the same parameter beta 1, it will have several powers also. So therefore, it is not a linear function, right? So that kind of models are called nonlinear regression models, functions, right? So what we practically try to do is we are going to in the regression in regression what we do is we try to model the expected value of y as a function of x. So that I will come to that a little later when we look at some examples. Okay. So now, uh, what should we do when we're fitting regression models? Well, first we can start with some exploratory data analysis, right? Especially we can look at scatter plot of y versus x, y versus x2, y versus x3, and so on. By from that way, we will be able to understand if there are clear uh, bivariate relationships with y and several x's, we can identify those. That is one thing. And also we can identify whether there are any relationship between x1, x2, x1, x3, x2, x3, between x variables. That also is going to be important later on when you are fitting models. So like that, we can first identify possible relationships between pairwise relationships existing between the variables that we consider. That is one thing. And then we can start fitting models by after understanding that possible relationships. There are actually, when you are fitting a regression model, it is important to have enough data. For example, if your model contains, say, 2 parameters only, right? Still, you need about 30, 40 observations to get a good model, right? For each parameter that you want to estimate, you need to use several observations, right? So thereby, depending on the number of variables included in the model, the number of required observations will be large. If the number of variables increases, number of observations should also be large because you'll have to estimate several parameters using the data. So anyway, when you are fitting a model, usually it's good if you can at least divide your data set into two parts called training set and validation set, where you use the training set to fit the model. and then validation set to validate the model. So don't use all the observations that you have to fit the model. Right. So that's for that also we need a reasonably large data set, because in order to fit the model, or you need enough data, and then to validate also you need some observations, not as many as for fitting the model, but at least some reasonable number of observations, right? So divide the data into training and validation sets before fitting and selecting a regression model. The available data should be divided into at least two parts. The first set is called the training set, which is used to fit the candidate regression models, right? And then validation set, which is used to assess the predictive performance of the fitted models on the data not used for fitting, right? Otherwise, if you use the same data that you use to fit the model to check uh, the performance of predictive performance, usually for the same data, predictive performance is high anyway, right? But what you need is a good model which will be suitable for other data also. When you have other x values, you should be able to accurately predict y values for those x values also. Right? So that is the idea. And in addition to that, sometimes if you have a sufficiently large data set, a third set called the test set may also be used for final evaluation after the model has been selected. Right. So usually these first two are used to fit the model. Fit not only one, actually. You usually fit several models, and then uh, select several models, and then maybe out using those models, you apply those models on the validations data set, and then from those you say select one model out of those previously selected models. You select one model based on the predictive performance. Right. In addition to that, if there is another data set, that will be good, right? Once you have selected the final model based on the previous two data sets, final model also can be tested with the test data. That is not always done, but if you have large enough data set, that also can be uh, done. So fit candidate regression models using the training set. Right? Those are the several possible models will be looked at. Several candidate models may be fitted using the training data. These models may differ in the explanatory variables. Those different models may have different variables included in them. Different transformations may have been used. Maybe in one model you have X, in another model maybe you have log X, and that kind of separate different possibilities you look at. And then some models may have interaction terms, that is the product terms. Some may not have interaction terms. Some may have polynomial terms. Some may not have polynomial terms, and so on. You uh, try several models and then check the adequacy of each of those models using the validation data. Actually, you have to check the adequacy of the fitted models before that also, because model as adequacy has to be tested for those fitted, selected models. And then based on those things, you will reduce the number of models that you are going to consider, right? So model adequacy refers to whether a fitted model is suitable for explaining the relationship between the response variable and the explanatory variables. The following techniques may be used to assess the adequacy of a single regression model. So adequacy, whether the model is adequate to describe the relationship between y and x's. That is the question, adequate. So several things can be used for this purpose. One thing is residual plots. Residual is the difference between the predicted or fitted y value using the model and the actual y value, right? So you have observations, you have y values, right? Using the model, you can find out the fitted y value and you have the actual y value. So the difference between those two is called the residual. So residuals should not show any systematic pattern if the model is adequate, right? So what you do is you look at the residual plots, you plot the residuals versus different x values, for example, right? And then if there are some patterns that you see in the residual plots, that means that the remaining residuals can further be modeled by X. That's what it means, right? So therefore, the model that you have already fitted is not adequate. You can further improve it. So in order to check whether the model can be further improved by adding several other terms or several like spare terms and so on, to see whether that is possible, residual plots are useful. So, and also residual plots are used to check the assumptions regarding the regression model. We will talk about those things later. So that is a big important part. Residual analysis, we call it, right? Because when you are later on doing some inference, there will be some test of hypothesis carried out regarding the parameters. And those test of hypothesis, or finally the p-values that we look at, will be meaningful only if the model assumptions are satisfied, right? We will talk about model assumptions a little later. So in order to test the model assumptions, this residual analysis is important, right? We will use normal probability plots, for example, to check whether the residuals are normally distributed, because there is an assumption regarding the error terms in the models are normally distributed. So we check whether the error terms are normally distributed or not by checking whether the residuals are normally distributed or not, right? So that will be very important, because this assumption about normality is very important for the validity of the p-values of the t-tests and f-tests that we carry out in regression. So plot of residuals against the time order, right? We plot the residuals if for example, the data have been collected over some different time points, or if the data points have been collected according to some order, right? First observation must be, second observation must be followed by the first one, and so on. Then we plot the residuals against the time order or the order in which the data are collected, to check whether there are any patterns left there. If there are patterns left, then we have to include, for example, time or the order in which the data collected into the regression model as a variable to improve the model. And also residual analysis is important to identify outliers and influential observations. Uh, for that, we use something called leverage values, studentized residuals, Cook's distance, that kind of measures to identify whether some observations are outliers or influential observations. Cook's distance measures the influence of an observation on a fitted regression model. Smaller values are preferred in this case. Large values indicate observations that should be investigated carefully. And also in regression, especially in polynomial regression, and when several x variables are highly correlated, there is some effect called multicollinearity effect on the regression model, which makes the fitted model very unstable. That occurs because of some mathematical properties that is happening when, for example, X variables are highly correlated, uh, or something called multicollinearity occurs. Right? So, in order to check whether the multicollinearity exists, we have to look at something called variance inflation factors, denoted by VIF. So, if VIF values are larger than 5, then we say mild multicollinearity exists. If it is greater than 10, we say it's a severe multicollinearity exists. Right? So, in that kind of situations, models may be unstable in the sense that if you just change one or two observations, the model may change a lot. The coefficient, fitted the coefficients will be changed by a large amount, or sometimes even the sign of the coefficients may change. Right? So that's what you mean by unstable. Right? In a stable model, if you just change the values of one or two x variables slightly, the model doesn't change that much. Right? But if when the multicollinearity exists, that kind of things can happen. Right? So that therefore that kind of models are not suitable for practical purposes. The model is very unstable. So in that case, there are certain things that we can do to avoid multicollinearity or reduce multicollinearity or remove the multicollinearity and get a better model. We carry out several tests to check the adequacy of the model. One test is the overall F test. In the overall F test, what we do is we check whether uh, all the coefficients of the x variables are zero or not. Right. So that means practically this means we are checking whether at least one x variable that we have considered is important in modeling y, right? Or otherwise, are all the variables that we have considered, are all the x variables that we have considered are not important, right? So in this case, we are testing whether the coefficients of x1, x2, x3 up to say, suppose you are considering k variables, then we are checking simultaneously whether all of those coefficients corresponding to the x variables are zero, or at least versus at least one of those betas is not equal to zero, right? So why this hypothesis is important? Well, what we are trying to find out is whether uh, the y variable can be explained using x variables, right? So if all the beta coefficients are zero, that means the model will not contain any x, right? So practically that means any of those variables that we have considered are not useful in modeling y, right? So first of all, we look at that, right? Only very rarely actually this hypothesis will be accepted, H naught will be accepted, because we consider those variables usually because we have some idea that at least some of the variables, x variables that we consider will be useful in modeling y, right? So therefore, most of the times this null hypothesis will be rejected, and therefore we will decide that at least one of those beta j's is not equal to zero. But anyway, in almost all regression analysis, this test is done automatically, right, as the first test. So the test used for this thing is called a F test, because it is really the region is taken using a F quantile, F value, right, in a F distribution. That's why we call it a F test, right? So in the output there will be something called P value, right? If the P value is smaller than 0.05, usually we reject the null hypothesis and therefore accept H1. So in that case, if the p-value is smaller than 0.05, then we decide that out of the x variables that we have considered, there is at least one x variable which is important, which is useful in predicting or modeling y. Right? So therefore, after that, we have to find out which variable is that, and then uh, use that variable or variables to model y. Right? And thereafter, what we do is we uh, fit the model, whatever the model that we think is suitable, and then uh, we test individually each parameter, whether each parameter is equal to 0 or not individually using individual t-tests. Right. So this is another part that automatically given in the computer output when we fit a regression model. Right. So the first one is overall left test output, and the second one is usually individual t-tests. Right. It will give you the fitted coefficients, and then also testing whether the population parameters coefficients are 0 or not. Right. So there are also for each, you will have a p-value. So p-value, if the p-value is less than 0.05, usually that means corresponding H0 will be rejected. For example, suppose it says for the second parameter, beta 2 say is equal to 0 and beta 2 is not equal to 0. So if the p-value is, let's say 0.01, then we reject the null hypothesis that beta 2 is equal to 0 and thereby accept that, say that second variable beta 2 is not equal to 0. Therefore, x2 will be an important variable, right? So sometimes people call a significant variable, right? So like that, you select out of the variables, x variables that you consider, you select the variables with significant coefficients, non-zero coefficients, right? And then you refit that model. And then for that model, then all the coefficients that you have selected will be significant because you have removed the non-significant variables and therefore you will have the significant variables. So now you check whether how good is that model. So in order to check how good that model is, goodness of fit, we say. Goodness of fit, in order to test the good, measure the goodness of fit, there are several measures available again. One of the commonly used measures is called the coefficient of determination. It is denoted by R square, coefficient of determination. This is a measure of the proportion of the total variation in Y explained by the model that you have fitted. Right? Suppose, for example, the total variation or the total variance, for example, here we are looking at the variance as a measure of the variation. Suppose the total variance in Y is, say, for example, just to take a round number, says 100. And suppose, so that is only without using any X values. If you just look at the variance in all the Y values in your data, suppose it is 100, just to take a value. Suppose after fitting the model using X variables, then you calculate R square. Right? R square will give you a smaller value than 100 in that case. Actually, it measures the proportion of the total variation. So at the beginning, there was 100 variation. So now, say, for example, the model is able to explain, say, 30% of that variation. So only 30% of the variation, right? So then R square will be 0.3, the proportion, right? If the model is able to explain that variation out of the 200, if it is able to explain 80% of the variation, then R square will be 0.8, right? So this explaining means after fitting the model, some variation is still in the residuals, right? So that how much is that variation we can look at, and then we can look at the difference between the earlier variation and the variation in the residuals. So that difference will be the the amount of variation explained by the regression model, right? So R square is equal to, it's given as 1 minus SSE divided by SST. That is the same as SST minus SSE divided by SST. So this SST is the total variation, total variation. So when you SSE is the variation in the residuals, right? So SST minus SSE will be the difference. Originally, there was a total variation in Y. SSE is the remaining variation in Y after fitting the model, in the residuals, in other words. So therefore, the difference will be attributed to the model. So we call it the variation explained by the model that we fitted. Right? So therefore, R square will be then the proportion of the total variation in the response variable explained by the regression model. Right? So this is the variation in the response variable at the beginning, and SST minus SSE will be the amount of variation explained by the model, explained in the response variable explained by the model. Right? Uh, I don't know whether I mentioned it correctly. So SST minus SSE will be the amount of variation in the response explained by the model. And then when you divide that quantity by SST, we get the proportion of the total variation in the response variable explained by the regression model. Right. So if it is close to 1, that means the model has been able to explain a large proportion of variation in Y. So that is a good thing. So in that case, we say it's a good fit. Right. Otherwise, if R square is small or close to 0, that means our model has not a good job in explaining the variation in Y. So therefore, model is not a good fit, right? So like that, we can find out how good our fitted model is. But you have to remember here, R square will increase, or will increase to 1, right? Or it will be increasing. You can increase the R square by adding more and more variables if you into the model, right? And suppose, for example, you have a model with 5 variables, your R square is equal to 0.7. And suppose when you add several other variables, it becomes 0.8, right? So now the model with larger variable has R square 0.8, but in that case, of course, it has a large number of variables also, right? So in that case, it's not going to be considered as a good model, right? Because what we want is a model, simple model with a small number of X variables explaining a large proportion of variation in Y, right? That's what we call the parsimony principle, is parsimony. So we want to get a parsimonious model. Because remember, when you are using these models to predict Y, for example. So in order to predict Y, if you need large number of X variables, it's going to be very costly to predict, right? Because you have to get the observation from each of those X variables. Right? On the other hand, if you can do the almost the same amount of job, or same accuracy in predicting using a smaller number of X variables, that model will be better, right? Even the model with a little more variables has a large R square, larger than the previous one, like 0.7 and 0.8. Say 0.7, the model with R square 0.7 has 5 variables. But if you can increase it to 0.8, R square to be 0.8, if you add 5 more variables. But just increasing 0.1 in R square using another 5 variables will not be worth sometimes, because in order to get observations for those 5 variables will be very costly. The accuracy of the model will be increasing only by a small amount. So therefore, you have to balance these things when you are fitting the models. But anyway, R square is a very preliminary measure. So therefore, actually, because of this idea that I mentioned, that R square will be in general increasing anyway with the number of variables, the better quantity to look at is something called adjusted R square. So this is the quantity that you should look at. So this quantity actually adjusts for the increase of the R square when you are increasing the X variables, right? So that quantity is usually smaller than the R square, right? So adjusted coefficient of determination, R square adjusted, will be calculated by doing some adjustments, and that will be the most suitable quantity to look at to get some idea about the variation explained by the variation in the response variable explained by X variables, considering also the number of variables in the model, right? Conditioning on the number of variables. So that is the quantity that you should look at, not the R square itself. And then other quantities, right? So sum of squares of errors, which was also appearing here, right? Sum of squares of errors. Some people call it sum of squares of actually residuals, right? I'd like to call it sum of squares of residuals. These are not actually the sum of squares of errors. These are actually sum of squares of residuals. But from the beginning, most of the books and authors are using the word sum of squares of errors, right? So sum of squares of errors is equal to the squared values of the residuals, right? So that is called the SSC measures the total unexplained variation in the response variable after fitting the model, right? So SSC is equal. So these EIs are residuals, E1, E2, E3, and so on. Each residual is the difference between the observed Y value and the predicted Y value using the model, right? So is a large SSC will be give you a good model, or a small SSC? Yeah, a smaller value indicates a better fit, right? If a model fits well to the data, then it will be explaining the variation. Large proportion of variation in Y will be explained by the model, and therefore the remaining variation will be small, right? So that means good fit means small SSE. But it should be interpreted carefully when comparing models different number of explanatory variables. So if you are comparing two models to see which model is better, suppose, for example, one model contains three variables, the other model contains five variables. In that case, it's not good to directly compare SSE, because SSE will be reduced anyway when you are increasing the number of observations, right? But if that amount of increase is very small relative to the number of variables that you have included, that increase is not an useful increase or decrease in the SSC, right? If the amount of decrease in SSC is small when you are increasing the number of observations, number of number of variables in the model. I made a mistake there. So let me tell it again. If you are considering two models, one has, say, five variables, X variables in the model, the other one has, say, 10 X variables. In that case, it's very possible that SSE in the model with 10 variables is smaller than SSE in 5 variables. But the difference in SSE, the reduction in SSE is very small compared to the increase in X variables. Then the larger model will not be a good model. That cannot be considered as better than the smaller model. So therefore, instead of looking at SSC, it's better to look at something called the mean square error. So the mean squared error is given by SSC divided by n minus k minus 1, where n is the number of observations and k is the number of variables. right? So yeah, in that case, you can use MSE, mean squared error, to compare two models, even if they have different number of variables, because the number of variables have been taken care of in this case, right? So therefore, considering the number of observations as well as number of variables in the model. Therefore, this is a better method. So MSE, mean squared error, or some people call mean square residual, is another possible measure as a goodness of fit. Smaller value of MSE indicates a better fit. One disadvantage of this MSE is that it is in the squared units, mean squared error, right? So it is very difficult to interpret this value to understand what this really means, right? So therefore, even more better or something easy to understand is something called the residual standard error. Residual standard error. That is the square root of the mean squared error. And this will have the same units of the data, y variable, the same units of the y variable. So if y's are in, say, kilograms, this will also be in kilograms. Right? So therefore, it's easy to interpret, right? So a smaller value of residual standard error indicates a better fit. Right? So that means the fitted values will be closer to the observed y values. Fitted values means fitted y values are close to the observed y values. So how do we compare two or more adequate models? Now, suppose you get one model, it is adequate, you think it's adequate relative to adjusted R square and relative to based on the residual standard error, you select that as an adequate model. You have another model maybe containing some other variables and some other transformations of variables. You consider that also as an adequate model. Maybe same, roughly the same R square, roughly the same residual standard error, and so on. So then, how do you compare these two models? Model comparison should be done after checking that the candidate models are reasonably adequate. If two or more models satisfy basic adequacy requirements like adjusted R square and then uh, this quantity residual standard error, then additional criteria will have to be used to select a model as the final model, right? So adjusted R square is used, right? If R square was used earlier, now you can look at adjusted R square, but I think at the beginning also it's better to look at the adjusted R square. And in addition to that, of course, several other criteria. One is called Akaeki Information Criterion, AIC. Right. So these criterion usually used when you are selecting a model out of several adequate models. Right. So this AIC, the formula is given here, but for you that is not necessary. What you should look at is actually when you're comparing two models, for the two models, AIC values will be there. The smaller AIC indicates a better model, right? So you can compare the two AIC values. And also there is another criterion called BIC, Bayesian Information Criterion. Bayesian Information Criterion. For that also, the smaller value gives you the better model, indicates a better model. And then there are other measures, one called Mello's CP value. Mello's CP compares the candidate model with a full model, right? So you have now selected the adequate model. It compares with the full model, means the model containing all the X variables that you would like to consider. So that is the model called full model. So you compare your full model with the model that you have selected as the adequate model, right? Usually the adequate model will not have all the variables in the full model, right? What you try to do is actually select several best set of variables out of out of all the X variables that you consider, right? So a good model usually has a small value of CP, preferably close to the number of parameters in the model. Right. So the criterion to look at is whether the value CP value is close to the number of parameters in your model. So suppose, for example, number of parameters in your adequate model is 3, then you expect the if the model is good, then CP to be close to 3. Right? Suppose you have one model with 3 variables, CP is like 3.5. You have another model with another 3 variables, or maybe some of the variables are in common, but still 3 variables. For that, suppose CP is like 10. So then definitely uh, the model with CP close to 3 will be better out of those two. And then there are other measures which depends on the prediction error. Prediction error, right? So the prediction error is equal to y hat minus yi hat. So that is the same as the residual. Residual is the remaining amount after doing the prediction, right? So this yi is the observed value of yi hat is the value coming from the model. So difference between that is the error, right, in the prediction. So this measure is called uh, RMSE, root mean squared error. Root mean squared error. That is actually the mean of the squared errors of your observations, right? Squared errors of your the predicted values. That's called root mean squared error. So here, this one is actually having, this has quadratic terms. Therefore, the units will be the quadratic squares of the data. So, for example, if your y values are in kilograms, this quantity, oh, sorry, this is the root mean square. Yeah. So, therefore, you take the square root. So, therefore, the root mean square error, you'll again have the same unit as the original y unit of the original y values. Otherwise, if you consider the mean squared error, the square root will not be there. That will be in squared units and will be difficult to interpret. So that's why we usually call root mean squared error. Square root of the mean of the squared errors. And the other quantity is called MAE, mean absolute error. Mean absolute error. So yi minus y hat is the error. When you consider the absolute value, this is always positive. So you are adding them and dividing by the number of terms in the model, number of y values in the model. That gives you the mean absolute error. So for both, you would expect for a good model, these numbers have to be small, right? So if you are comparing two models, you can look at RMSE and MAE for the both models and then select the model with smaller values, model with the smaller root mean square over smaller MAE values. And then other methods are based on cross-validation errors. Cross-validation estimates how well the model is expected to perform on new data, right? So all the previous ones were done based on the same data that we used to fit the model, right? But sometimes the model may be giving you good values or acceptable values for the measures of the goodness of it for the when you are applying it for the data for which that you use to fit the model. They are maybe small AIC, small BIC, small root mean square error, and so on. But if you apply the same model for the new data, new X values, then you also have actual Y values for those observations, but you have not used those data to fit the model. So that's why we call it new data. Right? So when you fit the models, the same models, two models, and get the predicted, and you don't have to now fit the model, you have the model actually. So if you apply that model, two models for the same new data, right, for the new data, you can get the predicted values, y values. Right? So remember, I made a mistake there again. You don't fit the model with the new data, you have the model with the previous data. So now you apply that model to the new data, new X values. You substitute new X values and get the fitted Y values from those models, and then look at the difference between actual Y values and the fitted Y values, right? So if the model, for a model that is good, that model should have those root mean square error, root mean absolute error, and so on. Small values for the new data also, right? And there are some other tests called nested F tests, right? To compare several models, right? Suppose you have a model with 5 variables, and you now see whether you want to see whether one of these variables can be dropped, because you like the model to have smaller number of observations always and have a good predictive power, right? So in order to test whether you can safely drop one variable without changing the predictive power that much, in that kind of situations, you use something called F tests. They are called nested F tests. Right? Here I'm giving you a very brief description only. There are theory behind all these things. And most of the times people don't apply all these things. At least several of these things have to be applied. So this is what you call the parsimony that I mentioned earlier. The principle of parsimony means that among several adequate models, the simple model should usually be preferred. Simple is preferred. Simple means uh, uh, mainly a smaller number of X variables. Right? A parsimonious model contains only the important experimental variables and avoids unnecessary complexity, like large number of powers and then uh, transformations, right? Very extreme transformations are going to be difficult to understand the model, right? To interpret and so, right? Sometimes you can get a good model if you include very, very complex terms, right? Very, very complex transformations of X variables. But then in that case, you don't know what it really measures, right? So it's always good if you can include the variables which have practical meaning, right? So for example, suppose you are considering the amount of water or the ratio of water. So suppose that variable is W, but you can consider also if you want e to the power W or log W or something, some other term. But then e to the power W is difficult to interpret, right? Log W may be difficult to interpret. On the other hand, W may be a variable for which log W has a better meaning, right? So in that kind of situations, including log W may be better than including W, for example. Right. Okay. So practical interpretations are also important, and the number of variables in the model has to be a manageable and small number of variables also better. Right. Now, several other things that you have to consider in fitting regression models. Overfitting is not a good thing to happen. Right? Overfitting means sometimes when you are considering the training set, right? When you're fitting the model using the training set, you may be able to get a very good model with very high R square value and R square adjusted value and so on, very high. Because you have included large number of X variables in the model, right? But if you apply the same model for the validation data, your R square will be very low or very much lower than in the previous situation. Right? So that happens because you have fitted the model, overfitted the model for the training set. It's only, right? That model is not good in general, in practical situations, right? For that training data set, that model is very good. But it's not going to be good in general if you are going to apply that model for other data, right? So therefore, overfitting like that for a particular data set only is not a good thing, right? Overfitting occurs when a model fits random noise or the unusual features in the training data rather than true underlying relationship. An overfitted model may have a very high R square and a small training error, but it may perform poorly in the validation data. So how do you detect whether there is an overfitting problem? Right? Detecting overfitting. Overfitting may be suspected when the training error is much smaller than the validation error. So training error for the training dataset, when you apply, error may be very, very small. Or on the other hand, adjusted ASCA will be very, very high. But when you apply the same model for the validation data, training error may be quite large. So that may be a effect of the overfitting. For example, a model with a very small training root mean squared error, but a large validation root mean square error may be overfitted. So the final model selection, right? So you have considered several models, looked at several criteria as a goodness of fit. The final model should be statistically adequate, right? So first of all, it should be an adequate model, reasonably simple, interpretable, and should have good predictive performance on the validation data. That is an important thing. Having a good predictive performance only on the training set is not a good criteria, right? So final model should be statistically adequate. That means high R square value for the performance of the validation data and other measures you can look at. Reasonably simple, that means the number of observations, number of variables. So number of variables is a manageable amount, number. And also practically also you have to think, suppose one model has maybe two variables, but they are very expensive to measure those variables. Another model may have maybe three variables. You get the same predictive power from both models, but the second model for the variables, you can easily get. The cost is low, right? So even if there are three variables, if it is giving the same predictive power as the other variable, it may be the best model practically, right? So you have to like that consider practicality as well as statistical considerations when you're selecting the final model. Therefore, model selection should not be based only on R square, which I have seen in many applications. I will show you later. Most of model selection has been based on only R square. It should also consider residual diagnosis, adjusted R square, AIC, BIC, validation error, parsimony, and practical meaning of explanatory variant. So there are so many criteria, things to look at when you're selecting a final model because you are going to use this model practically anyway. Right? These are not done for fun, right? Usually you have to spend some money to get the data, right? And then apply the model substitute the data into the model and get the predicted values and so on, right? So that is kind of a theory part, important part about fitting a regression model, right? How to, what are the things that you have to consider in fitting a regression model? So I will take a small break actually. I will stop this part of the video here and then I will discuss in the next part uh, as an initial explanation of fitting the models, right? So we will first fit a model, a simple linear regression model, or bivariate relationship, fitting a model for the bivariate relationship. And then we will go into multiple linear regression model, right? So that will be discussed in the next part.